Okay, let's get back to DFAs. Any questions about... Talk to me after class. Any questions about DFAs? So when we talked about the formal definition of a Turing machine, what did we start defining right after that? Not quite to there yet. Well, how about like how a machine actually does computation? So we formally defined this configuration thing, and then we defined computation for a Turing machine as a sequence of configurations, right? So in fact, we should do the same thing here. What does it mean for a DFA to actually compute something? So do I actually need this configuration thing now? Well, do I have a tape now? No, so should I need a configuration? No. Well, let's see. What things do I actually need to actually carry out a transition? Just a single state and a single character. I don't need the rest of the tape to figure out, okay, now I'm going to move right, and now something else is going to happen. I have exactly one thing I can do. So in fact, the definition of computation is much simpler. So let's see. So suppose that the input looks like this. So it has n characters, let's say. For a Turing machine, I might not know how long this is going to run for. I don't know how many transitions I'm going to apply because I may change the contents of the tape. But for a DFA, how many transitions am I going to apply? N transitions, because I have n characters. Oh, that tells me how many states I'm going to see. How many states am I going to see? N? N plus 1. Why? So right at the beginning, before I've read any character, how many states have I seen? 1. So that's where the n plus 1 actually comes from. So in fact, we can define computation based off of the states that we see along the way. So a computation for a DFA, M, let's call it, on input W, and let's call it W1 through Wn, like usual, is a sequence not of configurations now, but of states. And let's see, let's just think about it for a second. So let's give it some names. These a sequence of, and we just figured it out, is exactly n plus 1 states. So we actually know how many states we're going to actually see. So let's give them names, R0, R1 through Rn. But if I just tell you in any old sequence of n plus 1 states, is that a proper computation for a DFA? Is it okay if I'm at some state right here and instantaneously the next state in the sequence is this state way over here that's not connected to Q0? Is that okay? Am I allowed to jump states without going through the arrows? No. So we need to restrict what types of sequences we're allowed to see. Well, let's see. Can the starting state right here, R0, be different from the start state? Can I start in a different place than the start state? No, that doesn't really make sense. So in fact, we need to say something about what these R states are. Well, let's see. Well, it's a sequence of these states. Well, the first one, R0, better be the start state Q0, because if it's different, then we just made something that doesn't make sense, right? It doesn't start in the actual start state. Well, let's see. How if I want to go to state Ri, what state should I come from? Or Ri minus 1, right? So I'm going to leave a little bit room. Well, let's see. How do I get from the previous state to the next one? Transition. Well, what character am I actually going to look at in the input W here? Wi, right? Because in R0, so in that case, I would be 1. So what character to go from R0 to R1 should I look at? W1. So in fact, well, let's see. How do I look up? I'm in state Ri minus 1. I'm looking at Wi right now. So how do I look up? Yeah, Ri is the next one. Where do I look that up? In the transition function of the machine. So remember, M has these 5 parts, right? It has the transition function there. And because it's a total function, I'm guaranteed that I get a next state. So it's not like I stop in the middle, like a non-deterministic Turing machine, for example. I'm guaranteed a next state. So in fact, since there's exactly one state to go to, I just look up in the transition function the state I was in and the character to look at, Wi, and it better be the case that the next state, Ri, is the one that's next in the after the transition's applied. So if I apply from R sub I minus 1 to the character Wi, I better end in R sub I. So just as an example, so let's look at the input for the DFA we made earlier. Let's look at 0, 1, 1. Well, what is the sequence of states that I visit here? What is the start state that I visit first? Q even. So I'm going to abbreviate that to EE. Well, let's see. How do I know what state to go to next? I look at the first character, and I go, and what state should I look at? Q even, even. I see a 0. Now what do? I look up in the transition function, and I see, oh, the 0 took me over to odd, even. So the next state in the computation is the state that I landed in. Then I say, oh, I'm in odd even right now. What should I do? I look at what character? At the 1. Since the 0, I'm not going to ever see that 0 again. So I look at the 1, and then I say, oh, now I'm going to go down to odd, odd. Q odd, odd. And then that character's gone now. Q odd, odd. Now I look at the next character, which is a 1. And so what state do I go to? Back up to odd, even. So odd, even. Do I have any characters left to read? No, so should I stop? Yeah, so once we finish the input, we always have to finish the input. But once we do, we stop, look at the state we're in. Am I in an accepting state now? Yeah, so should I say yes on 0, 1, 1? Yeah, so therefore we accept 0, 1, 1. And in fact, it's in this language anyway, so that's good. Does that make sense, computation? I see people shaking their heads. So does that make sense? Yeah.
So each state can be considered a configuration then?
So the definition for configuration would have to change because configuration, remember, involved the entire contents of the tape that we've seen. So if you define that to be the pair of the character that we just saw in the state that we're in, then yeah, you'd be right. But it would have to change, of course.
So we don't need any computation is only comprised of states,
Mhm.
right? So,
That have the property that it must be the case that the right transition was applied between the states.
and since we don't have any of the other things of the tape on there, I don't quite get how we can know. Well, I guess.
Well, we fix the input right here.
Yeah.
So once we fix the input, then the computation is fixed.
Okay.
So in fact, it makes it a lot easier. If we didn't fix the input, then we don't know what sequence is going to happen. Question in the back?
Yeah. If you know like all the states, but like configuration, is it possible to like get the input back?
No, because, for example, a great question. So what he was asking was, if I tell you the sequence of states that we went through, so if I tell you these n+1 states, can you tell me what the input was? No, and why not? So think of this example. So if I have two characters on the transition. So here this doesn't mean C is 0, write a 1. It means two different transitions. One transition 0, one transition 1. So if I tell you, yeah, Q0 goes to Q1, which character was it? So in fact, you can't recover it. But in some cases you can, but in the general case you can. Other questions? Okay, so once we defined computations for Turing machines, then we talked about the languages of Turing machines and whether they were recognizable, decidable, and all that. So we note that DFAs can't run forever because we force them to stop once they've read through their input. So we actually don't need to have a difference between decidable and recognizable or something like that. So, which is nice. So the language recognized by DFA M is what you might expect. So all the strings that the machine M could be fed, such that M has an accepting. Oh, I should define that too. Has an accepting computation on W. What do you think accepting computation means in this context? Yeah. Yeah, so which of these n+1 states lands in a final state? Rn, yeah. So we should make an addendum to this. Accepting computation if Rn is a final state. It doesn't matter whether any of the other states were final, it's just the last one that counts. Okay? Does that make sense? So what you might expect is just the language of M is just the set of all strings that it accepts that land in a final state. So it's very analogous to Turing machines. And we say that language L is regular if some DFA recognizes it. So the language from before about the odd zeros and even ones or something like that, that is by definition a regular language because I have a DFA that recognizes it. And so now what we would want to know is what languages are regular, which ones are not. Because if you can model a system using a DFA instead of a Turing machine, then obviously a DFA is a lot better because you have less information to store. But if you can find that it's not regular, then we need to think about the language a little more. So what you might expect is let's try to merge the idea of decidability with DFAs now. So we talked about A sub TM, A sub LBA, and then now let's talk about A sub DFA. So A sub DFA. So it's exactly the same as before, but now M is a DFA and accepts W. So what do you think? Is this decidable or what? In fact, go ahead. Right, it must halt, right? So you can just run the machine on the input, just check the final state at the end, see if it's a final state. Super easy. What's another reason why this is decidable that I just thought of? Well, think about it. Are DFAs just LBAs in disguise? Well, a DFA is a particular type of LBA that just always moves right and just stops when it sees the end marker, right? So in fact, DFAs are a special case of LBAs, but we found that A sub LBA is decidable. So it must be that A sub DFA is decidable for that reason. So in fact, this is decidable because we can just simulate M on W and check if resulting state is in F or not. Okay, so that's not too surprising because it's just a simpler model of a LBA. Any questions on that? Yeah.
Question on the part of the language recognized by DFA.
Mm-hmm.
To me, it seems like it should be that
It's the computation?
that it's decidable, not recognized.
It's just an unfortunate notation. It should be decided, yes, but it's just an unfortunate notation thing. We're always going to use recognized, except in the case of Turing machines where you have to make a distinction, because all the models other than Turing machines we can force to halt. So in fact, it will always be recognized. It's just unfortunate notation.
So then we're never really going to be in a situation if we're comparing a Turing machine to a DFA and then we're talking about decidability.
Right, yeah. The only difference that will ever happen for deciding and recognizing is only with Turing machines. Yeah, yeah, so it'll always be recognized. Yeah, I agree with you. It should be decided though. Other questions about this? Okay, well, what was the other problem that we talked about with LBAs that turned out to be undecidable? It was not A sub LBA, but it was E sub LBA, right? Because we reduced it from ATM to this. So you may think, well, what about the emptiness problem for DFAs? Is that still undecidable or what? So let's talk about that problem. So what do you think? Yes, it's decidable or undecidable? Oh, come on, you have a 50-50 shot. What do you think? Decidable, who says decidable? Who says undecidable? Come on, like 80% of you didn't vote. It actually turns out to be decidable.
Shouldn't we say recognizable?
Decided by a Turing machine. Yeah, so decidable here, decidable will always mean Turing machine receives input and halts.
Okay.
We won't say like DFA recognizes this language. We'll say this language is regular. Yeah, so it's just only in the definition we need to have that there. You had a question in the back? Yeah.
So is it anytime we're doing in like a DFA or anything like that, those are always Turing machines as well?
Yes, so a Turing machine receives a DFA and an input encoded somehow, and then just simulates the DFA. Or like in the LBA case, it receives an LBA, and it simulates the LBA in the way we talked about in the lecture.
Do you run a DFA on a DFA?
No, because if you had to run a DFA, you need to store those two things, the state and the character that you're reading. But in a DFA, you can only remember one thing, which is the character. Yeah. I can't hear you.
Isn't that just the same thing as if there is a path from the starting state to the
Exactly.
any
So he's got it. So why is this decidable? If there's some way to get from the start state to some final state, is the language empty? No, just pick any character along the transitions that lead to that final state. Did I just make a string that the machine accepts? Yeah, so in fact, we can use our 310 knowledge to solve this problem. So treat DFA as a directed graph and check if any path, any directed path, I guess, from Q0 to any state in the final states. If there is a path, so if so, then there must be some string that the machine accepts, and so therefore the language is not empty. So therefore we should reject, because we just showed the language of the DFA is not actually empty. And then if not, if there's no path from any state, from Q0 to any state in F, then that must mean the language is empty. And so we should accept. And of course, this is decidable because the directed graph is a finite thing. And we know algorithms like breadth first search, for example, that halt in a finite amount of time. So in fact, this is decidable too. Yeah.
Does that mean that any DFA that was run by a Turing machine would be decidable? Or is there an example?
A particular DFA is not decidable, a language is. But given a DFA, we can check whether it accepts anything or not.
I guess I'll maybe word it. I mean, like in that situation, we have like, let's say we had all. So,
Also, DFA is the same situation.
yeah, so it's
But-
if you're using a DFA as
But you need to check that any state that you can reach is a final state. Because if there's a state that you can reach that's not a final state, then take any string that takes you there, then that's a string that the machine does not accept. And so therefore it doesn't accept everything. There's actually a much easier way to think about it that in terms of closure properties that we'll get to eventually. Yeah.
How could it be a state that's not, if it could end at any point in the string, how could it be a state?
No, it has to read the entire input. So remember in the definition of computation, note that there are n+1 states here. So I have to read the entire input. Yeah. Good question, though. Other questions? Okay. Cool. So, in fact, there must be, therefore, some language that an LBA can recognize, but a DFA can't. Because the fact that eDFA is decidable already kind of tells us that. Okay. So, let's get back to that question that was raised about all sub DFA. So, all sub DFA seems kind of related to the emptyness question, whether it says no on everything versus it says yes on everything. So what we're going to talk about are regular operations. So the regular here, I should say, The word regular we're going to use, I think, in 4 different ways. So the regular here does not mean regular language. It just means the term regular in like literature means some kind of pattern that repeats over and over. So if you think about it, if you run a DFA for a long enough string, then eventually you're going to see the same state over and over and over, right? If you have the string be long enough. So the fact that it's regular here versus the regular language definition does not mean anything. They don't have anything to do with each other. So remember, what does closed under an operation mean? We defined it for Turing machine languages. What did that actually mean? If I have some operation and I say a bunch of languages are closed under that operation, what does that actually mean? Right, so if I apply that operation, union, whatever, to any set of languages in this set I'm talking about, decidable languages, for instance, then I will get a result that's also decidable or recognizable or something like that. So in fact here, can we say, well, if I apply the complement operation to a regular language, do I still get a regular language? We showed that it was true for decidable languages, that if I give you a decidable language and I look at all the strings not in that language, that is also decidable because we just switched the QAccept and the QReject states. So in fact, what we'll show here is that regular languages are closed under complement. Another way to say this is if L is regular, then it must be that L bar is also regular. Okay? How do you think we might be able to prove that? It's actually very similar to the Turing machine decidable complement one. So what did we do with the Turing machine deciders and showing that the decidable languages are closed under complement? What did we do? What did we do to the actual machine? We swapped the QAccept and the QReject states, right? Because we guaranteed the machine always halted. And so if it landed in QAccept before, it lands in reject now. And if it landed in reject before, it'll land in accept now. What do you think we should do here? The same thing. Do DFAs always halt? So if it lands in a final state before, it lands in a non-final state now. So if I accepted it before, do I accept it now? No, I say no on that string. If it landed in a non-final state before, did it land in a final state now? Yeah, so therefore, in fact, I get the complement. So the proof is for any DFA for L, swap final and non-final states. And you can prove this formally. So if the computation on a particular string lands in a state not in F, now it'll land in a state in F, and vice versa. So this one should be quite easy. But any questions about that? Okay, so for decidable, we started off, I think, with union and then did complement. But I started with a complement here because it's the easiest one to think about. The next one we'll talk about is, let's see, so I remembered I have to talk about something else, but I'll get to that. So regular languages are closed under union. So can I get a decider? So this is a different question. Can I get a decider to decide the union of two regular languages? So what do? Take the DFAs for both languages, and whatever input the decider gets, run the first DFA on the input, run the second DFA on the input, and then just look at the final states that the state that you land in. If you land in a final state of either one, then say yes. If you don't land in a final state in either, say no. So in fact, we can decide the union of two regular languages. But this is a different question. This says, if I have the union of two regular languages, the result is regular, meaning that there's a DFA for it. But can a DFA run two different DFAs on the same input? No, why not? Well, I can only see the input once. Once I see the input is gone. That sucks. So what do? Maybe we can try to combine the DFAs somehow. So maybe let's give definitions to help us out. So let L1, L2 be regular languages, and let's say D1, D2, I actually should give the names of the 5 parts. So let's say Q1, same alphabet for a different reason. Some transition function, some start state, some set of final states, and analogously for D2. So just give names to them because we're going to actually use them. These are DFAs.
Oh,
Yeah.
sorry.
Yeah. I was just giving an example to show that you can't apply the same reasoning as we did for deciders here. Any other questions about this? Okay, well, let's think. Well, I only get to see the input one time. So if we can find in some way to run both machines in parallel, then we'd be all set. We can just simulate both machines at the exact same time since we see the input exactly once. What's the problem with that? What does run in parallel mean in this context? We don't have a tape to work with. If only we had some way to record all the possibilities that both machines can be in. Oh, wait a second. For computation, let's go back. What thing do we have to remember? What is a computation first off? The sequence of states. Do we have anything else to work with that we need to store other than the state that we're in? No, we don't need to store anything other than the state we're in. Well, let's see. What are all the possibilities that the first machine could be doing versus the second machine? Well, the first machine could be in any one of its states, and the second machine can be in any one of its states, right? Oh, is that a finite number of possibilities? Each one of these for each one of these. Let's model each one of those possibilities as a state. Okay? So model the possibilities as states, and then connect the possibilities based off how both machines would have done the transition. So we're going to make, I promise there will be an example, because there's a lot of stuff that'll follow. So let's make a DFA, let's call it D, and remove the subscript. Let's call it Q0 here. Well, let's see. Should I take into account all the possibilities of Q1 and Q2? Or could there be some that I could remove? In general, I don't know whether I can remove some of the possibilities. So might as well just include them all, right? If we're wasteful on the number of states, that's fine. As long as it's a finite number, I don't care. Well, let's see. All the possibilities of the first machine coupled with all the possibilities of the second machine. So is there a nice compact way I can write that? Not union, because that's all the possibilities of Q1 or the possibilities of Q2. I need and here, not intersection either. Cross product, right? Because any possibility here coupled with any possibility over here. So it's in fact Q1 cross Q2. So it's very analogous to, say, the transition function for DFAs. The Q cross sigma, all the possibilities of any state with any symbol. So same thing here, any state in Q1 coupled with any state in Q2. So what are the objects in this set? So it's obviously a set where I have some, let's make it Q prime. Q prime's a state in the first machine, and Q double prime is a state in the second machine. What are the types of things that live in this set? Because it's a cross product. Ordered pairs, right? So it's actually an ordered pair, Q primed with Q double primed. So that's actually kind of important for the rest of the definition to make sense. Well, we handled the states, that's good. The input alphabet is exactly the same, that's also good. So 40% of the way there. What about the start state? What state of the first machine should I start in? Q1. So the first coordinate of this pair, because Q0 is an ordered pair, because it's a state of Q, should be the start state of the first machine. And what do you think the second coordinate should be? Q2, the start state of the second machine. Okay, so we handled that. Oh yeah, that's right. So let's handle the transition function next, and you'll actually see why I'm doing the transition next. What are states in this machine? Are they just normal states, or what are they? They are 2 words, which involve things called ordered pairs. So the transition function for a DFA takes a state and a symbol. What are states in this machine? Ordered pairs. So the first thing in here should be an ordered pair, coupled with some, shouldn't look like a Q, let's call it B. Although it looks like a Q upside down, I guess. Okay, let's see. What does the transition function for a DFA have as its output? So it takes a state and an input. What does it give us? A state. What are states in this machine? Ordered pairs. So the output should be an ordered pair. It's actually going to be a big ordered pair. Trust me, I've done this. Okay. Well, what's going to go here? Well, I'm trying to simulate both machines at the same time. So the first coordinate involves which of the 2 machines? The first one. So this first coordinate should entirely deal with the first machine and not the second one. So I'm trying to simulate the first machine. What state of the first machine was I in before the transition occurred? Q primed, single primed. And what symbol am I looking at? B. Oh, how do I figure out what state to go to for the first machine? Look at the transition function of the first machine. Okay? What's the transition function of the first machine called? Delta 1. Awesome. So delta 1 of Q primed with B. I just asked the machine D1, hey, I'm in this state, I see this, where do I go next? And that's what I put as the first coordinate. What do you think the second coordinate is going to be? Delta 2, Q double primed with B. Awesome. And so we're 80% of the way there. What is F? The set of final states, of course. Well, let's see. What operation are we working with here? Or are we trying to make a DFA for? Union, right? So if the first coordinate is a final state, do I need to look at the second one? No. What about the other way? Second coordinate's final. Do I need to look at the first one? No. So it's either the first coordinate is a final state in the first machine, or the second coordinate is a final state in the second machine. Awesome. So in fact, we will look at all of the pairs, the ordered pairs, in our set of states, such that Q primed is a final state of the first machine, or the second coordinate is a final state in the other machine. I just look at every state in this machine I'm making, ask which one is a final state of their respective machines, and if at least one of them was a final state before, I make this one final. What about go ahead.
Why is F not just F1 union F2?
Union, first of all, for union, that would be a set of states, union a set of states. So the result is a set of states. This is a set of ordered pairs. So it wouldn't be of the right format. And first of all, because it needs to have that second coordinate with it. So you can thank him later for me writing this. Another way you can write this is F1 cross Q2. Let's see, yeah. Union F2, no. Q1 cross F2. That's a formal way of writing it. Let's see. Other question, yeah.
So if we're able to get, if D1 is able to get to D2's final state, then that means that...
That's not possible. So we'll insist that Q1 and Q2 have nothing to do with each other. So they're just disjoint machines to keep things easy. Other questions? Yeah.
The start state of this union Q0 should be Q1 prime, Q1 double.
Well, I'm looking at the start states of the original machines. And so these have to link to those, yeah. That's the reason for that. Other questions? This entire construction, ignore F for a second. The other four parts, did that have anything to do with union? No, it only had to do with the final states at the end. So let me ask you a question. What if I change this to intersection? What would I have to change about the machine that we just made? Oh, only F. So what would it be for intersection? That's a formal way of writing it. That's correct. But for the English description, what would I have to change to make it intersection? And, yes. So in fact, we can get quite powerful results here. Anyone know what symmetric difference is? Only I do. Anyone know what symmetric difference is? Yeah. Yeah, so it's the set of strings that are in exactly one of the two parts. Instead of union where you have at least one, a symmetric difference is exactly one. It's like XOR. So our regular language is closed under symmetric difference. So what would I have to change about our English description? So in this case, it would be or, but not both. So anyone have a formal way of writing it? So you can thank me later. So it's the one for union, but I'm taking away the ones that are in both, which is the intersection one. That's just a formal way to write it. But the key here is that the vast majority of the construction only depends on the structure of the DFAs. It doesn't have to do anything with union intersection. Only the final states matter here. So this whole construction from start to finish is what's called the product construction. Meaning because it's a cross product between the states and in some cases the final states. Any questions about that? I promise I have an example. Or the notes have one, yeah.
Why couldn't we have done the same strategy that we did with decidable languages and deciders under union?
But because we only see the input one time for DFAs. Because we always move right, so we only see the input once. So we can't run it twice on two different machines.
So like, why can't we just, if we're looking for input in the union, we just run through one machine, and if it's there, do it, and then run through the next
Well, that means I'm running through the input twice. The DFA can't store anything other than what state it's in currently and what symbol it's reading. If there was some way that a DFA could duplicate the input, then that would be possible, but there's no such operation. And so therefore it can't be. So you need to build that into the states. And we can because we know there are only a finite number of possibilities that both machines could be in, because you only need to keep track of what state you're in. Which makes this a lot easier than, so there's no way to do this for a decider because you need to be able to handle the configuration at a given point because that'll change. Whereas a DFA, if you visit a state multiple times, it's the exact same thing. It doesn't remember the past. Other questions? Yeah, I have 12 minutes. Great. So let's do an example. So this one is from the notes. See if I can copy it down correctly. R0, that one's final. One and then back. What's the language of the first machine? Just looking at it. Can you figure out what language it is? Right, even number of characters, even length. Good. What about the second machine? So this one's a little more non-trivial. Well, it seems like it's all the strings that have a multiple of 3 number of zeros. So if it has 3 zeros, then I'm going to eventually go to R1, then R2, then back to R0. And then if I add another 3, it'll go back again. So essentially what we want to do is, for union, is all the strings that either are of even length or have a multiple of 3 number of zeros, or both. Well, let's see. If I want to do the product construction on this, how many states am I going to have? 6, because it's 2 times 3. So let's do that. So I'm not going to put the parentheses around because it just complicates things. But I'm going to put the names of the states. Let's see, Q1, R0, Q1, R1, Q1, R2. Oh, I should ask, Could a computer carry out this product construction? So you don't have to do it mechanically by hand? Yeah, and so the entire process of the construction didn't require any like thought as, okay, if this DFA had a transition here, then I need to do something special. It's entirely mechanical all the way through. So in fact, a computer can actually do this, and there are some libraries you can download if you wanted to make a computer do it for you, which is nice. So okay, so let's worry about final states at the very end. So what's the start state of this 6-state machine? The Q0R0 one. That's great. How many transitions are there going to be? We'll have 6 states, and how many for each? I got to see a 0 coming out of it and a 1 coming out of it. So in fact, I'm going to have 12 transitions. But let's see. Think about the one so we can carry this out by just looking at the machines back and forth, but we can actually make a lot of progress. Look at the 1 transitions. What about the 1 transitions on the first machine? What happens? It just goes back and forth, right? Because that's what it always does. What about the second machine? It stays in the same state. Oh wait, the reason I put this in this grid pattern is that the 1s will transition between the 0 row for Qs and the 1 row, and they'll stay in the same column. So in fact, the transitions for 1 will always do this. So in fact, we can sometimes just look at the DFAs and make the process a lot faster, which is really nice in this case. So now it's just the 0 transitions we need to worry about. Okay. What about Q0, R0 on input 0? So from Q0 on 0, where does the Q machine go? To Q1. So it's going to be in the bottom row somewhere. What about the top machine? It was in R0 before. Where does it go now? To R1. So Q1, R1. What about Q0, R1? Can you predict what's going to happen there? Well, it's definitely going to go to Q1's row. From R1, where does it go on 0? R2. So in fact, it's going to do this analogous thing by moving a column over. So in fact, you can kind of see in this product machine what the original machines were doing, because the 0s are going across the rows and over a column at a time, whereas the 1s are transitioning in the same column. They're transitioning in the same column. All right, across the rows. Okay, what about Q0R2? Well, it's definitely going to go down to the Q1 row.
Q1R0.
Q1R0, so it's in fact going to come all the way over here. Okay. What about the Q1 row for 0s? What do you think is going to happen there? Can you just predict what's going to happen? Yeah, it's going to go, instead of top going down to the right, it's going to go up to the right. So in fact, the transitions are going to look like this. So the Q1R2 is in fact going to go up and right, but over here. So in fact, this is a lot easier than working with deciders and thinking about where the tape head is. You just think about what does the state represent and how do the states relate to each other. Are we done with this machine? Yeah, we need final states. So what operation are we doing in this case? Union. So what state should be final? Well, anything with Q0, because if it has Q0 in it, I don't care what R state it has. So the entire first row is all final. I should have done them in a different color. Okay, well, are those all the possibilities for final states? Anything with R0, but we've already handled the Q0 one, so the only other one is this one. So in fact, this is what we have. So I'm going to let you go a little early, but I want you to think, so this is a nice Piazza question for this DFA. Is this the smallest DFA for this language? So can you find a smaller DFA for this? So I'll let you think about that, and I'll see you on Monday.